Hi, in this video I'll explain the somewhat complex concept of angular momentum in relation to moment of inertia and torque. In this disk which is rotating in front of us, you can see a tangential force F, a velocity V, and a curved blue arrow which denotes the angular velocity omega. Now let's look at what's the difference between angular momentum and moment of inertia. They sound pretty close. Once a body is rotating, the angular momentum is like a linear momentum, but for rotation, so it keeps it rotating. Like something caused the earth to start rotating millions and millions of years ago and is still rotating, and it will continue to do so unless stopped by an opposing torque. Thankfully, there is no opposing torque for earth. The moment of inertia depends upon the shape and size of the rotating object. So if it's a sphere like the earth or a disk, it will have a different moment of inertia, and it depends on how far the masses are from the axis of rotation. That's why you have an mr squared out there in the equation. To derive the equation, we need to take several masses on that disk. So let's take a small particle on that blue patch shown by a red dot. Let it be mass m1 at a radius r1 from the center of rotation. Similarly, on the green patch we choose a particle of mass m2 at a radius r2. Now, in general, we have chosen a mass mi at a radius ri, and there are lots of such masses on that disk. The linear momentum of any such mass would be pi is equal to mass into velocity, that's mi into vi. But we know that velocity itself is equal to r omega. When we substitute that into the top, we get pi is equal to mi into ri omega. Now, angular momentum itself is like a linear momentum of a particular mass into the radius of action. So when you multiply both of them, you get Li is equal to Pi into Ri, like a torque is force into radius, something like that. So Li becomes equal to Mi into Ri omega into Ri, that's Mi into Ri squared into omega. You notice that there is no omega I because omega is constant. Now we have to sum up the angular momentum of all the masses on that disk. So that capital L is equal to sigma I is equal to 1 to n of each Li. So Li is L1, L2, L3, L4 and so on. So inside the brackets we get Mi into Ri whole squared into omega. There is no omega I, so omega can be taken out of the brackets, and inside the brackets we would have M1 R1 whole squared plus M2 R2 whole squared plus M3 R3 whole squared plus so on till n. That's nothing but the total moment of inertia of that object. So that's L is equal to omega into capital I, or L is equal to I omega. Now a brief explanation of the units. So I is moment of inertia, that's mr squared. So m is kg, r is meter, so you get kg meter squared. Omega, angular velocity, is radians per second or 1 by second. So when you multiply all that, you get kg meter squared by seconds. That's the unit for angular momentum. Now in terms of vectors, we must understand very clearly that only the linear vectors like force, velocity, linear momentum, they are the tangential guys. And you can see the arrow direction for F and for V. And you can also see the top view of that disk shown as a circle. These vectors lie in the plane of that flat circle. Now the rotational vectors like omega, torque and angular momentum need a consistent direction. They can't be going round and round that disk like the tangential vectors. So here in this sketch you can see that all those three vectors, the rotational vectors, are pointing upwards along the axis of rotation because the axis of rotation is consistent and is not changing every second. If that disk is rotating clockwise, the same rotational vectors would point downwards along the axis of rotation. In this way, it makes mathematical sense because all of them are cross products. Now, if you take an example of angular momentum, it's a cross product of linear momentum and the radius vector or the position vector. The linear momentum is in the plane of that disk. The position vector, the radius vector, lies along the plane of that disk. So when we do a cross product, the angular momentum comes out as perpendicular to both P and R, and that's why it's along the axis of rotation. Now if you look at an analogy, P is equal to mv, you can see L is equal to I omega. That sounds pretty close and also easy to remember. Now there's a relationship between angular momentum and torque which is not so obvious. So we have to start with finding the rate of change of angular momentum with time. That's nothing but delta L by delta t. That equals I into delta omega by delta t. That's nothing but I alpha, where alpha is angular acceleration. But we know that torque is equal to I alpha. Therefore, the rate of change of angular momentum with time is equal to the torque. I hope that this video was useful in terms of conveying the nuances of moment of inertia, angular momentum, and torque, and that you're able to understand all the concepts of the rotation. Thank you very much and have a great day.